For years, I have been dubious of arguments that the universe must be teeming with microbial life, but what I'm about to tell you today changes things. The typical argument for optimism leans on the remarkable fact that life appears to have emerged on the Earth rather quickly. The most indisputable evidence for this comes from microfossils, which we can perform radiometric dating. This is the gold standard right now. In 2006, William Schopf reported the discovery of a collection of such fossils found in the apex chert deposits in Western Australia, with the oldest of them dated to a staggering 3.5 billion years ago. A decade later, this record was beaten by Alan Nuttman and colleagues, who found fossilized bacterial mats known as stromatolites in southwest Greenland and dated them to 3.7 billion years ago. For context, the Earth formed just over 4.5 billion years ago, and soon after was almost obliterated in a collision with a Mars-sized planet that formed the Moon. That sterilizing impact sets a definite lower limit for life's window of opportunity. But we can reasonably squeeze the time frame a bit more by noting that when the Earth first formed, it was an absolute hellhole covered with oceans of lava and under continuous bombardment. Since all life on Earth requires water to survive, the earliest evidence for oceans provides perhaps a better starting point. By studying ancient minerals known as detrital zircons, Simon Wilde and colleagues reported in 2001 evidence for the first ocean at around 4.4 billion years ago. So on our timeline of Earth's chronology, we can see that indeed the fossil evidence appears relatively soon after the conditions become suitable for life. In the 4.4 billion year history of a habitable Earth thus far, life appears within the first 700 million years. It's easy to grab onto those numbers and assume that therefore life is an easy process. Indeed, in a commentary article that was tacked onto Nuttman's original fossil discovery paper, Abigail Allman commented that it shows that life is not a fussy, reluctant, or unlikely thing. But this is all old news by now, and many of you know that I have not bought into this conclusion when confronted with those same numbers. But why? It really all comes down to the subtle influence of selection effect. On our timeline, it seems to have taken evolution at least 3.7 billion years to go from the earliest forms of life to a technological civilization, as in us. Let's assume for the moment that this is normal. It typically takes 3.7 billion years for all of that evolutionary jazz to take place. So if life started immediately with the oceans, then the earliest intelligence could have developed would have been 700 million years ago. Now, let's imagine progressively later start times for life. As we shift along, we'll eventually hit a wall. As seasons like the fall remind us though, the Earth will not remain habitable forever. Something has got to give. And in a classic paper by Caldera and Casting, they calculate the death date at 900 million years from now. This is not the sun going giant and gobbling up the Earth, but rather another effect that I'll discuss later in the video. The real takeaway here is that the latest point at which a civilization like us could emerge would then be 900 million years from now. And if evolution takes 3.7 billion years to do its thing, then life would have to start no later than 2.8 billion years ago. Any later than that, and there simply would not have been enough time for us to emerge. What this means is that life has to start early for us to be here and be talking about it. It's quite possible that there are countless Earths around sun-like stars where the emergence of life takes much longer to get going than it did here, and that's all well and good. But we could never evolve on such a planet. There simply wouldn't have been enough time. In this scenario then, life's early start is not statistically interesting. It is a necessity to our very existence. This is why Allwood's conclusion is premature, in my opinion, because it misses this key selection effect, also known as the weak anthropic principle. Now, in all fairness, I don't know that the evolution timescale is 3.7 billion years all of the time. Let's imagine it was in fact much shorter, say 900 million years. Now, the latest that we could start life and still have time for us to evolve would be today. In this scenario, the fact that life started at the very beginning of this long interval is interesting. In this case, I would agree with Allwood. Yes, life's early start indeed implies that it is easy. However, it has to be said that this scenario would be pretty odd. It would mean that on most planets, evolution happens way faster than it did here on the Earth. Hopefully, the real point of this whole discussion is that when we try to make inferences about how easy abiogenesis is, that's the spontaneous emergence of life, it cannot be divorced from assumptions about how long evolution takes. In statistical parlance, we would say that the two of them are covariant. A few years back, I wrote a paper that applied a rigorous Bayesian framework to this whole question, accounting for this covariance. I won't discuss how I did this in detail here, but rather I'll direct you to my previous video on the topic. It's actually one of the papers that I'm most proud of, not only accounting for this covariance effect, but also employing some elegant statistical theorems to yield a result which is robust to choices that one might make during such an analysis. And that's a technique known as objective Bayesianism. But here's the punchline, is that we can express the odds ratio between two hypotheses with this simple formula. In the first hypothesis, life is, as Allwood would say, a quick and easy process. If we reran the tape, it would almost certainly pop up again. In the second, abiogenesis is a rare and unlikely event. Here, the timescale to expect a success is much greater than the age of the Earth itself, and thus, on most planets, it never succeeds. Of course, given enough monkeys on typewriters, it will occur in some places, and naturally, we would live on one of those planets where it did, else we wouldn't be here to talk about it. Again, this is the weak anthropic principle in play. So if we take the timeline that I showed you before and plug in the numbers to my equation, it suggests that the easy life scenario is 3.8 times more likely than the hard scenario. That might sound promising, but it's actually not what we would normally consider statistically significant. Usually with these odds factors, we would only consider numbers greater than 10 to 1 before we would really start believing them. In the news, just like science, it's often hard to know what to believe, but that's where today's sponsor, Ground News, can help out. Ground News is a website and app that pulls together related headlines from around the world. Every story shows you all the related articles in one place with a visual breakdown of the political leaning, reliability, and ownership of the reporting outlets. There was a story in here this week related to today's video, reporting on how a giant meteorite strike 3 billion years ago could have actually kick-started evolution by stirring up deep water iron and releasing phosphorus into the environment. On Ground News, you can see how different partisan news outlets are reporting this, so here we have fairly even coverage. You can also see the bias distribution and the publication ownership details, giving you a clearer picture of where your news is coming from. Ground News is the brainchild of former NASA engineer Harleen Cower, and like me, they firmly believe in the value of objectivity and exposing yourself to other views. For example, a killer feature is the blind spot tab, which highlights stories that you'd miss if you only read the left or right-wing papers. This is the best way to get your news, folks. Clear, transparent, and unbiased. So head to ground.news/coolworlds to save up to 40% off the unlimited access Vantage plan that I use. Once again, that's ground.news/coolworlds. Now back to the video. So 3.8 to 1 odds in favor of easy life is encouraging, but we can actually find some even earlier evidence for life that changes things. But this evidence will not be direct evidence like fossils. In 2015, Elizabeth Bell and colleagues suggested that there is evidence for life in 4.1 billion year-old zircon deposits. Although they don't see fossils, they can measure the various ratios of elemental isotope abundances, and in particular, the ratio of carbon-12 to carbon-13 was found to be anomalously high. Now, both isotopes appear in nature, but living creatures prefer to soak up carbon-12 simply because it's lighter and easier to work with. If we accept this evidence, it shifts the odds from 3.8 to 8.7, so pretty good, but still not crossing the 10 to 1 threshold we'd normally want to see. Now, since my last video on this, there have been 2 studies published which really shake up the odds, and also a third study published which doesn't actually change the odds, but is still really important to mention. So let's start with that one. A provocative 2019 paper by Gavin Schmidt and Adam Frank, who, by the way, are both Coolwood podcast alumni, suggested that humanity might not be the first technological civilization on this planet, as my analysis certainly assumed. They argued that a civilization could have emerged during the Carboniferous period, that's 350 million years ago, and really we just wouldn't know about it. Now, I should really do a video about this at some point, but fortunately, for the sake of today's video, it actually doesn't really change things. You see, that time interval is in fact pretty tiny on the scale of Earth's entire history, and so the numbers come out the same either way. In fact, you can even push this date all the way back to the emergence of complex multicellular life, which surely is a prerequisite for a civilization, and it still doesn't change anything. So fortunately, we just don't have to worry too much about this for today's video. But a result which definitely does rock the boat is another revision to the earliest evidence for life on Earth, but this time coming from a genetic analysis. In a tour de force paper by Edmund Moody and colleagues published in Nature this summer, they claim to be able to date the age of what is known as Luca, the lowest universal common ancestor. All life on Earth shares a common ancestor, evidenced by our universal genetic codes, machinery for protein synthesis, and shared chirality of the almost universal set of 20 amino acids. But how long ago did this Luca live? The authors perform a time analysis of pre-Luca gene duplicates, and they time calibrate them using microbial fossils and isotope records. Now, this is definitely not my expertise, but the result is critical for our story because it gives a date of 4.2 billion years ago. This is really squeezing life up against the start time now, plugging in their result, the odds shift to 13-1 in favor of an easy abiogenesis scenario. For the first time, we can formally say that we have strong evidence in favor of this hypothesis. But this is just one of two papers, remember. The other one applies pressure to the opposite end of Earth's chronology, the death of Earth's biosphere. For more details on why this point even exists, check out my video, Watching the End of the World, a personal favorite. But for the sake of this video, let's just do a quick summary. As the sun ages, it becomes gradually more luminous. Now, this is nowhere near enough to explain the recent climate change, but over 1 billion years, it would translate to a 10% increase in luminosity. As more energy is dumped into Earth's atmosphere, the rate of evaporation and thus precipitation increase. Rain dissolves carbon dioxide out of the air, forming a weak carbonic acid, and that acid then reacts with minerals and rocks to form solid carbonates, essentially the weathering process. So this means that CO2 is being pulled out of the atmosphere over very long timescales, and is in fact one possible geoengineering solution if we can figure out how to speed it up. But the very, very long-term consequence is that as the sun heats up, the CO2 is depleted from the atmosphere. Now, obviously, too much CO2 is a bad thing, but too little is a problem too. And in a classic paper by Caldera and Casting, they predict that it would drop below 10 ppm in 900 million years from now. That's a level that they claimed would be so low that photosynthesis would be impossible, causing most of the biosphere to subsequently collapse. This end date, 900 million years from now, is way before the sun swells into a giant, and it obviously affects Earth's total habitable window, a critical parameter in my own equation. So when I saw a new paper by R.J. Graham that greatly revised this estimate, I was very curious to see what they found. R.J. highlights that since Caldera's paper back in 1992, that's over 3 decades ago, we've learnt a lot. For example, in the original paper, the authors assumed a strong dependency between the rate of weathering and the temperature, but since then, a bunch of work indicates a much weaker effect. Similarly, there's a good case that some plants can still photosynthesize at levels below 10 parts per million CO2, especially C4 plants, which have a CO2 concentration mechanism to really help them out. So this new paper argues that 2.9 parts per million is a more reasonable lower limit. But besides from CO2, we also need to think about temperature because, of course, plants can also die just of heat stress. Caldera and Casting thought that the hot limit would be about 50 degrees Celsius, but some plants actually do thrive at that temperature. For example, there's a desert perennial called Tidstromia oblongifolia, which grows exponentially in the Death Valley during summers that often reach this temperature. In addition, although it's not a plant, cyanobacteria are capable of photosynthesis at temperatures up to 74 degrees Celsius, so at least in principle, plants could adapt to a hotter climate. In the end, this new paper estimates a toasty 63 degrees Celsius, that's 145 degrees Fahrenheit, as a more viable upper limit. Putting this all together pushes the lifetime of Earth's biosphere out to as much as 1.8 billion years from now. That's double the original estimate. It's an astonishing number when you think about it. Multicellular life, animals, the Cambrian explosion, dinosaurs, humans, all of that happened within the last 500 million years. On this scale, all of that is just recent history, and there is potentially 3.5 times that left to go for evolution to run rampant. One cannot help but be in awe of the unimaginable possibilities that lie ahead for our planet long after we're gone. Coming back to my equation, using Gray-Madau's value extends the odds even further to 15 to 1. It is 15 times more likely that life starts easily than slowly. Finally, the data appears to have overwhelmed the weak anthropic principle. However, one concern here is whether a civilization could truly emerge during this late endgame phase of the Earth's biosphere. I mean, could we imagine a civilization that survives on just desert shrubs only? There is probably some point before this end date where the kind of agriculture needed to support billions of large animals like ourselves becomes untenable. To see this, let's try putting the odds ratio of fast to easy abiogenesis on a graph plotted against the habitable lifetime of the Earth. Here you can see the odds we get with Caldera's original lifespan and the data we had before. That gives an odds ratio of 13, as well as Graham's revised lifespan, which gives us an odds ratio of 15. Now let's repeat this calculation for a range of values, going as small as 4.4 billion years, which is essentially assuming the world will end tomorrow. Interestingly, no matter what we assume, the odds factor is always greater than 11.3, with a minimum occurring at 4.6 billion years. So that would mean the latest time we could have emerged would be 200 million years from now. But even this 11.3 number is still a high odds ratio and would still be qualified as strong evidence. Is there any way that we could somehow engineer this down? One idea is that we could try invoking the Silurian hypothesis, thereby shifting the earliest allowed civilization to the Carboniferous period. But again, this gives us an odds factor of at least 10.4. The most extreme case I can imagine is a civilization appearing during the Cambrian explosion. That's literally the very start of complex life, but even this has a minimum of 10.0. It is still strong evidence. So I think this is actually a really profound result. If Luca's 4.2 billion year age stands the test of independent scrutiny, then it essentially establishes that the easy life scenario is now strongly favored. And that is a fact which is robust to essentially any plausible change which we might try to impart on the other parameters. Despite all of that, I still have reservations about the claim that life is common in the universe more broadly. You see, my analysis explicitly assumes an exact Earth, rerunning the tape if you will. But even exoplanets with similar masses, radii, and orbits to our own will surely be very slightly different. Different chemistry, different internal structures, different water fractions. Perhaps then the Earth is an incredibly rare example of a Goldilocks planet, a unicorn, as the rare Earth hypothesis would suggest. Whatever our opinions about that idea, and yes, I have many opinions, we certainly cannot rule it out. The key question then is how similar to the Earth does another planet have to be for this easy life scenario to be valid? There's probably no way that we can answer that using the Earth alone, but instead we will need to turn our telescopes out to other worlds. I maintain that it's important to be consciously and forcefully agnostic in this quest, but at the same time, I cannot help but feel a wave of excitement about this news because it means The universe really could be teeming with simple life, and just think about the prospects of what that means for searching for intelligent life out there. So, until next time, stay thoughtful and stay curious. Thank you so much for watching this video, everybody. I hope you enjoyed it. If you did, be sure to hit that like button and subscribe. Those two little actions help us out. If you can afford it and you think we're worth it, one of the best ways to help us out is to become a supporter to my research team, the Cool Boys Lab, using the link down below and up above. And that way you can actually support our research program to make videos like this and the actual calculations and research that go into it. So please do check that out, and I'll see you in the next video.